Acids, as we all know, are sour in taste. Some of the important examples that we use in our everyday lives include acetic acid, which is obtained from vinegar. We have citric acid, which is present in all the citrus fruits like lemons, hydrochloric acid, nitric acid, sulfuric acid can be some of the important examples for acids. Bases, on the other hand, taste bitter and they can be considered the chemical opposite of acids. Some important examples include potassium hydroxide, sodium hydroxide, which is commonly used in the preparation of soaps, and ammonium hydroxide. According to Arrhenius theory, acids always increase the concentration of hydrogen ions in an aqueous solution, thereby making the solution acidic. By increasing the concentration of H plus ions in a solution, the pH will drop, and this is what makes it acidic. Okay, let's take a simple example. An aqueous solution dissociates into H plus ions and the corresponding anion. Now, the hydrogen atom that has lost an electron is considered a proton. H plus is basically a hydrogen atom that has lost its single electron. Now, coming to the Arrhenius definition of bases, bases increase the concentration of hydroxyl ions in an aqueous solution, thereby making the solution basic. So, by increasing the concentration of OH minus ions, the pH of the solution is going to increase, and this is what makes the solution basic. Again, a general example would be, so dissociates into B plus plus OH minus ions. Again, this is in a aqueous solution. So it is these hydroxyl ions that are released that will increase the pH of the solution. Now, most of the acids and bases that we know are highly corrosive in nature, that is, they are known to destroy other substances and can even burn our skin. As it is impossible to taste every solution to determine whether it's an acid or a base, we have something called acid base indicators. So, acid base indicators help us to determine if a given solution is acidic or basic in nature. So, the most commonly used one is litmus paper, which is a natural acid base indicator obtained from lichens, and it can change its color depending on the acidity or the basicity of a solution. So, if you take a solution, an aqueous solution of, let's say, HCl or sulfuric acid, so we know that these are acids. So, when we put a blue litmus paper in acidic solutions, then the blue litmus paper will turn red in color. when we dip a blue litmus paper in acidic solutions like HCl, sulfuric acid, or even nitric acid, then the blue litmus paper will turn red, indicating that the solution is acidic in nature. Similarly, let's take a basic solution which can be potassium hydroxide or sodium hydroxide. Now, if we were to insert a red litmus paper here, then it will turn blue. So a red litmus paper will turn blue if the solution is basic in nature. If it is basic in nature. So acid-base indicators help us to determine if a given solution is acidic or basic in nature. HCl, or hydrogen chloride as it is known, is a colorless gas which is not acidic when it is dry. But when we dissolve HCl in water, then hydrochloric acid will dissociate. So HCl in an aqueous solution is going to dissociate into its constituent ions, which is H plus and Cl minus. So hydrochloric acid has now ionized to form two ions, and as ions are produced in water, HCl in an aqueous solution can actually help to conduct electricity, and this is because of the ions that it has generated. Similarly, we take the case of sodium hydroxide. Sodium hydroxide can be considered an alkali because it is a base that is soluble in water. All the bases that are soluble in water are considered alkalis. So when we put sodium hydroxide in water, sodium hydroxide, it's going to form Na plus plus OH minus ions. Again, because ions are released, it can conduct electricity. And because OH minus ions are increased or released, they increase the pH of the solution, and hence sodium hydroxide is considered a base. Another important topic is strong acids and bases. So HCl, nitric acid, and sulfuric acid are all examples of strong acids. So HCl, as we discussed before, when we put it in water, the HCl is going to undergo complete dissociation into H plus and Cl minus ions. For example, if we were to drop 1000 molecules of HCl in an aqueous solution, then all the 1000 molecules would completely dissociate and they would exist as H plus and Cl minus ions. And strong acids, increase the concentration of H plus ions because the molecule has completely dissociated. So you would see a increase in the number of H plus ions. Okay. Similarly, acetic acid, formic acid, and carbonic acid are examples of weak acids. So when acetic acid is put in an aqueous solution, now this is important because it is a reversible reaction. So acetic acid can dissociate to form acetate ion plus H plus. Now it's important to note that for weak acids, the extent of dissociation is minimal. So if we were to take 1000 molecules of acetic acid, only a few number of molecules would have dissociated into the ionic form. And even if more molecules ionize, because the reaction is reversible, they are going to combine again to form the parent molecule, which is acetic acid. Okay, so in the case of weak acids, if you were to put them in an aqueous solution, you would find more of the undissociated molecules in the solution compared to the dissociated ions, and this is why weak acids usually produce less number of H plus ions. The same concept can be applied to bases. So we would have a strong base and a weak base. Sodium hydroxide is a very strong base. Sodium hydroxide, potassium hydroxide can be considered examples of very strong bases. So when you put it in water, sodium hydroxide is going to dissociate into Na plus plus OH minus ions. So 1000 molecules of NaOH is going to completely dissociate into Na plus and OH minus ions. So a strong base is going to increase the concentration of OH minus ions. Similarly, if we were to take a weak base like ammonium hydroxide, again this is a reversible reaction, and if it dissociates, the ions would be NH4 plus plus OH minus ions. Again, because the reaction is reversible, the products formed can again combine to form the reactant again. So any weak base when put in an aqueous solution would have more number of undissociated molecules than the ions. So weak bases will generally produce less number of OH minus ions when compared with strong bases.